Now that we've talked about the significance of the first derivative and the second derivative, I want to put everything together and talk about using information from both the first and the second derivative to sketch functions. So remember the first derivative, where the first derivative is positive, we know the function's going uphill to the right, and where the first derivative is negative, we know the function's going downhill to the right. We know the second derivative tells us about concavity, how the curve curves, whether it's concave up with a curve with a cave in the top, or it's concave down with a cave in the bottom. So let's take a look at the kind of problem that we're going to do several times until we're quite good at. So consider the function x cubed minus 3x squared plus 3x. And I want to do a number of things, the last of which is going to be to sketch the curve. So find the largest open intervals upon which f is increasing and decreasing. Secondly, find and classify as relative max, relative min, or neither, all critical points. Third, find open intervals upon which f is concave up and concave down. Oops. Fourth, find all points of inflection. Fifth, something that you could have done before you ever came into a calculus class, but it's an important part of graphing anyway. Find all intercepts. All x and all y intercepts. You know exactly how to do that. And last, sketch a graph, good graph, of the curve y equals f of x. Okay, so let's take a look at part A and part B. Part A talks about where the function is increasing, going uphill to the right, and where it's decreasing, going downhill to the right. And part B talks about critical points, places where the derivative either equals 0 or doesn't exist. And both of those have to do with the first derivative. Part C and D. Part C talks about intervals upon which the curve is concave up and concave down. And D talks about points of inflection. Both of those have to do with the second derivative. So we are going to need both the first and the second derivative to be able to answer this question. Let's start with the first derivative. F prime of x equals, this shouldn't be too hard after some of the derivatives we've done, 3x squared minus 6x plus 3. Let's do a sign chart for this. For f prime, let's set this equal to 0. Let me just write set f prime of x equal to 0. So we have 3x squared minus 6x plus 3 equals 0. It's perfectly safe to divide both sides by 3. That just gives us x squared minus 2x plus 1 equals 0. And this factors nicely as x minus 1 times x minus 1, in which case x equals 1. So x equals 1 f prime of x is equal to 0. And we can plug values in to the left and to the right of x equals 1 to figure out where the first derivative is positive and where it's negative. Let's go ahead and plug in a value to the left. How about 0? F prime of 0 equals 3 times 0 squared. We're again plugging this into f prime. Everything goes into f prime when we do a sign chart for f prime. F prime of 0 equals 3 times 0 squared minus 6 times 0 plus 3. That equals 3. That's positive. So it is positive to the left of that 0. And let's plug in a value to the right of 1. How about we plug in 2? F prime of 2 equals 3 times 2 squared minus 6 times 2 plus 3. That's 12 minus 12 plus 3. That's 3 again. That's also positive. This is a first derivative sign chart. I can use my up and down arrows. Remember to always put your arrowheads on the right. So up arrow, up arrow. Let's go ahead and answer parts A and B. Now, unfortunately, due to limited blackboard space, I'm not going to be able to leave the answers on the blackboard the whole time. But let's go ahead and put them up now. Find the largest open interval upon which f is increasing and decreasing. Actually, I think what we'll do is hold off on the answer until we have our picture up there, because I think the answer will be much clearer once we can see our picture. So let's go ahead and just do the work for C and D now. We're going to need a sign chart for f double prime. I'm going to keep my sign chart for f double prime and my graph all lined up. So I'll keep the x values all lined up. -1, 0, 1, 2, 3. So here's my f prime. F double prime of x is equal to 6x minus 6. We can set that equal to 0. So 6x minus 6 equals 0. So x minus 1 equals 0. X equals 1. So this thing, the second derivative, is also 0 at x equals 1. Let's go ahead and plug in numbers to the left and to the right. How about 0? F prime of 0 is equal to 6 times 0 minus 6. That's -6, which is certainly negative. And f prime of, pick a number to the right of 1, how about 2? 6 times 2 minus 6, that's 12 minus 6, which is 6, which is positive. So it's positive over here. Now I want symbols above my second derivative sign chart. I can't use the up arrows and the down arrows because the second derivative doesn't tell us about increasing and decreasing. I need some other kind of symbol. What I'm going to use are symbols that for concave up and that for concave down. So over here, minus, we know minus is concave down. Don't get confused here. Concave down actually looks like a hill because the cave is in the bottom. It's curving downwards. So it's concave down over here, and over here it's concave up. For your second derivative, do not use the up arrows and the down arrows because the second derivative doesn't tell you about increasing and decreasing. Is everybody with me so far? If not, go ahead and pause. You can run this section of the video again. Now that we have all this information, I think it's safe to get rid of the algebra over here. Hopefully you have this copied into your notes. Let's go ahead and do the work for E. So we haven't actually written down our answers for A and B and C and D yet. We'll do that at the end. We'll finish E and F. F will be our picture, and then we'll copy down our answers for A, B, C, and D. They're all basically right in this information we have right here, and we'll be able to see it on our picture too. So for E, find all X and Y intercepts. For your y-intercept, we're just going to set x equal to 0. So y equals f of 0 equals 0 cubed minus 3 times 0 squared plus 3 times 0, which on a good day equals 0. So y equals 0 is our y-intercept. For our x-intercept, and there could be more than one, it could certainly cross the x-axis more than once. Let's set y equal to 0. So we'll set this whole thing equal to 0. X cubed minus 3x squared plus 3x equals 0. We can do a little bit of algebra there. We can see that we have a common factor on the left-hand side. There's an x we can pull out. So x times x squared minus 3x plus 3 equals 0. And when the product of two or more things is 0, one of them has to be 0. So either x is equal to 0 or this bracket's equal to 0. X squared minus 3x plus 3 equals 0. So either x equals 0 or that's equal to 0. That doesn't factor nicely. We can go ahead and use the quadratic formula on it. So x equals negative 3, which is 3, plus or minus the square root of negative 3 squared minus 4 times 1 times 3 all over 2 times 1. And that works out to 3 plus or minus 9 minus 12 is negative 3 all over 2. The square root of negative 3, of course, is not a real number. So this has no more real solutions. Really, this is the only real solution. So y equals 0 is our y-intercept, and x equals 0 is our only x-intercept. So we've answered E. We haven't yet answered A, B, C, and D, mostly because I don't have enough room on the board to put everything up at once, including all the algebra. So you can certainly rearrange things in your notes. Let's go ahead and do F. And now we get to see this process by which we synthesize all this information we have about the first derivative and the second derivative and our intercepts in order to draw a good picture. So when I draw my axis, my y-axis goes right below the 0 on my two sign charts, the one for f prime and the one for f double prime. And on my x-axis, I'm going to make everything line up as best I can. So I'm trying to put the -1 here underneath the -1s here. I'm trying to put the 1 under the 1, the 2 under the 2. All these x-axes are basically the same. I already know this thing crosses the x-axis at 0, the y-axis at 0. I know it goes through this point right here. Let's look on my two sign charts for f prime and f double prime to see the important points. Well, there's something interesting happening at 1. So let's go ahead and figure out what the y value is at x equals 1. So to make a x, y, at x equals 1, y is going to be, y is always equal to f of x. I'm just going to go ahead and plug 1 in here. So that's 1 cubed, so it's 1 minus 3 times 1 squared, 1 minus 3 plus 3, that's 1. So when x is equal to 1, y is equal to 1, I plugged into the original function because y equals f of x. So this function goes through the point 0, 0, and it goes through the point 1, 1. I've only plugged in 2 points. That's not a lot of information. For all we know right now, just based on those 2 points, maybe this curve is a straight line. I mean, we know it's not. But now let's go back to the information that we've derived from the first and the second derivative. So we start moving from negative infinity and moving to the right. So from negative infinity to 0, nothing changes. We're increasing and we're concave down, increasing on a hill. So we have to be going uphill the whole time, but it has to be shaped like a hill, not like a valley. Increasing on a hill, there's 2 ways you can increase. You can increase on a hill, or you can increase in a valley. You can see how this one's curved downwards, increase on a hill, increase concave down, and this one's increase concave up. We actually want this one. You can see from negative infinity all the way to 1, we are increasing. We are concave down, increasing on a hill. The curve looks like this, and it's level, it's horizontal right there. We have a critical point. So increasing, concave down, it levels out right here. Let's just draw that in as well as we can. Increasing on a hill, all the way to that point. We get all that information from the sign of the first and the second derivative. After that, we are still increasing. The arrow's going up again, but this time we're increasing in a valley. We are increasing in a valley. Again, both of these go up to the right. This one's increasing on a hill, this one's increasing in a valley. So after this point, we are increasing in a valley. I'll try to draw this as smoothly as I can, but it looks more or less like that. Increasing on a hill, followed by increasing in a valley. It levels off for a moment right here. Okay, let's go back and write our answers down to A, B, C, and D. So let's see, we already have our answers for E up here. The answer for A, let's read A carefully. Find the largest open intervals, possibly one, possibly more, so let me put the S in brackets. Find the largest open intervals upon which f is increasing and decreasing. I think it's pretty clear looking at this that it's not decreasing anywhere. Now I picked this function specially because we can very easily make a small mistake here. It might be very tempting to say the largest open intervals that this thing is increasing on are open interval from negative infinity all the way up to 1, and then another open interval from 1 to infinity. But there is actually even larger interval upon which it's increasing. Remember the definition of increasing. Increasing means that if you pick any 2 points, the point to the right is the higher of the 2. And I think you can see that this thing actually increases from negative infinity all the way up to infinity. If I pick any 2 points, the point on the right is always going to be the higher of the 2, even if 1 is to the left of 1 and 1 is to the right of 1, or if 1 happens to be 1 itself. If you pick any 2 x values, the point on the right is always going to be the higher of the two. So we don't want to go negative infinity all the way up to 1 and 1 to infinity. This says the largest open interval upon which this function is increasing, and it actually increases from negative infinity all the way to infinity, in spite of the fact that we have derivative 0 right there. So this is another one of those reasons I told you to be careful when we talked about the definition of an increasing function, that you can't say an increasing function is the same thing as having positive derivative. The definition of increasing does not mention derivative at all. Okay, so find and classify as relative max, relative min, or neither, all critical points. Again, we're just looking at the first derivative here. All the information for a and b is from the first derivative. So we have definitely one critical point where x equals 1. And even though we've gone ahead and are actually drawn the picture already, you can see the answer to b just from this sign chart up here. You don't need to see this picture down here to see the answer. You can see that we are increasing before we get to that point and increasing after we get to that point. This thing is not at the top of a hill. It's not a local max. It's not a relative max. It's not a relative min because it's not at the bottom of a valley. It's neither. So it's neither a relative max nor a relative min. If you write neither, I will certainly understand. We want to know where this thing is concave up and concave down. We can read all that information right off the second derivative. So on the second derivative, we can see it's concave down from negative infinity all the way up to 1. And we can see after that it is concave up. From 1 to infinity. And D, we want to find all points of inflection. A point of inflection is a place where the second derivative is 0. I mean, it's a place where it's differentiable, and we want the concavity to change there. So the concavity definitely changes from negative to positive, from hill to valley at x equals 1. So we have a point of inflection at x equals 1. We will be doing several questions like this, where I will give you a function, I'll ask you about where it's increasing and decreasing, find and classify the critical points. All of that comes from the first derivative. Then I'll ask you about intervals upon which the curve is concave up or concave down, points of inflection. All of that comes from the second derivative. I'll probably ask you about the x and the y intercepts. That's not calculus, that's just pre-calculus, but you should be very good at that by now. And then I'll ask you to sketch it. And even though I've done it out of order here, because I was very short on space, you can sort of do it in whatever order is most convenient for you.